Okay, everybody, good morning. It's 10 o'clock, so let us start again. I'm sorry that I have to cancel the class yesterday. Yeah, I didn't expect, but to be honest with you, I didn't expect that. Is that?
Is it okay to move to next Friday at 9 to 12?
Yeah, that's okay. That's okay. Yeah, perfect, perfect. Yeah, I didn't expect that, teaching 3 hours a day and every day is actually too much, exhausting. Together, I think it's also exhausting for you as well. When I was younger, that doesn't matter, right? But jet lag and I sometimes somehow I think the air or is that that this season have a lot of allergies? Any of us have allergies to the I don't know. Yeah, okay. So maybe it's just me. So I have, runny nose, itching here and yeah, itching in my nose and yeah, so it's better. So anyway, so I'm asking Professor Chung Hao that we're gonna move the class on Friday to next week as well, right? So we have at least one day off for you and for me instead of do every day 3 hours. I think that's a little bit too much. In the US, we every class, right? We teach 3 hours a week. So that means each week's only 2 days, and each day is only 1.5 hours. So here we we do like every day is 1 week. So, but anyway, so I think we it's good. The good thing is that I'm gonna stay here for 2 weeks. So I'm gonna be here for next week as well. I know that there's some disruption in your schedule. I'm very sorry about that. But we're gonna move 2 classes to next week. You already got an email from Miss Murphy, right? So our yesterday class was moved to Tuesday next week. And then our today class, I just talked to Professor Chung Hao. It's going to be moved to Friday from 9 to 12 next week. Okay, so any question before we start? So that's a little announcements that I like to make. I hope that the class is so far okay. Is it difficult or is it too easy? As usual, you are very silent. Huh? Yeah, so by the way, so the way that I look at deep learning is from more on applied mathematics point of view, right? Not from computer science point of view. So you see, that's why I call it scientific deep learning. We look at deep learning from mathematics, applied mathematics point of view in particular. So we're gonna see some mathematics, but like close to what you've seen, not computer science mathematics, right? Okay, so if there is no question, then I'm going to continue. So let us review what we did last time or 2 days ago. We looked at ReLU activation functions. We look at the generic neural network already, right? We look at the what we're going to do with that, how neurons actually try to mimic our biological neurons, and then how it actually is ordered into layer and layers, right? Um, and then you're going to say it's amazing, right? It's amazing that if you do in a feed-forward manners, actually you can approximate any function well. It's kind of amazing. So you notice that we do two things, right? R5 decomposition. Actually, let me go back here a little bit. Let me go back here a little bit to where was it? Oh, okay. Actually, I think this is the one. Yeah. So it's kind of amazing because why would this would work, right? And I'm sorry, which slide? I don't remember, but let me try to get there. Okay, here, right? It's kind of amazing because we put this in type composition from mathematical point of view. It's just a nonlinear composition, but it's in very specific manners, right? So you do alpha transformation and then nonlinear activation or composition and do alpha transformation and nonlinear activation function and again, right? From mathematical point of view, it looks so weird. And why would it work at all, right? So from the layout of, from the graph network point of view, It's a feed-forward network, right? Directed from one to the next and next to the next, right? So why would it work at all? That's the question that we try to answer. Or can that type of layout, R5 transformations and then nonlinear and then R5 and then nonlinear cannot approximate any function at all? So that's what we try to answer today. And we try to answer so for one particular rectilinear functions. And then I'm going to talk to you about how you're going to extend that to a more difficult, right, or more bigger class of activation function later. Chu Hao, do you mind get me some water? Yeah. So let me review what the rectilinear function is. Remember that this is a maximum of the input is z, right? So the activation function should keep the positive part and then zero out the negative part, right? That's very simple, and that's how it looked like RODU activation functions. And we have shown that, okay, first, of course, RODU activation function, the key is that it's piecewise linear, right? And then we actually show that if we look at this particular piecewise linear function, of course, it looks more complicated than RODU, right? Can we approximate, can we represent that with RODU? Yes, we can. We talk about that. And then we look at and then we actually roll it out as a network. You see that is a feed-forward, one hidden layer neural network that can actually represent that function exactly with RODU activation function. We talked about that last time. And then we look at a more interesting, which is linear, of course, right? Linear function is a piecewise linear. We expect that we can represent that exactly. I hope that you go home and check this is true. That is equal to h, right? I hope that you did. Please do so to convince yourself, which is, which gonna take you a second or so. All right, so then we see, okay, this, right? Max minus max here is nothing more than one single hidden layer neural network again, right? With two neurons in the hidden layers in a specific way. Then we can represent the linear function exactly with one hidden neural network. We showed last time. Okay, now we look at a more general piecewise linear functions, right? With m breakpoints, right? Piecewise linear have a number of breakpoint, and of course you have two slope at the end. So we have total m+2 information. Remember that, right? So we're going to use these m+2 informations to actually construct a rectilinear neural network that actually can represent this function exactly. Okay, so how do we do so? We actually mentioned last time we're gonna construct it in this manners, right? So this term is you put ReLU linear activation function at each breakpoints. Thank you, Chung Hao. We put the ReLU linear activation function at each breakpoints. So we have m breakpoints, so we have m ReLU rectilinear function. Okay, and then we have a specific rectilinear function on this side because on the rectilinear function x minus I have this slope, right? Have this slope. So in order to actually capture the slope here, we actually put a one more rectilinear function on this, right? With the reverse a1 minus x. So if the slope this way, then c0 gonna be non-zero. But if this way, then c0 gonna be could be 0 as well, right? And then h is necessary because when the function, right, the original function g at a1 is actually non-zero, then because all the rest of the term is 0, right? So we need h here to capture the like the elevation of the function, original function at a1. So we talked about that last time. Okay, now this is where we stopped last time, right? So this is the G function that we want to represent with the neural network, right? ReLU neural network. And this is our ReLU neural network right now, right? It's a linear combination of ReLU, which is good. We know that we can turn it into a network. I'm going to show you in a second. So our task is to determine these coefficients. So we have m plus 2, right, informations, and we have m plus 2 unknowns. We should be able to find m plus 2 equations to solve for these m plus 2 unknowns. So we talked about this, but let me repeat here. We're gonna put down every information that we have, right? So we're gonna look at the information at each breakpoint. At each breakpoint. So at x equal to a1, we know that our function g gonna be a1, right? This g a1, this height g a1. But at a1, on these is 0 because the rectilinear function, right? On this one is a 0 as well. The only non-zero one is h. So with the first information, you already determine exactly h. What is h, right? H is equal to GA1. In other words, if if there's no elevation here, then h is actually 0, right? So first equation allow you to determine h. Now we look at the second position, which is a2 here. So at A2, remember this, right? This guy, the first guy, right? The first guy is this. The slope is this, right? So as A2, which is here, right? So this is going to be 0. Everybody see that, right? This function is 0. So the first, this one is 0 at A2. Everybody see that? And on this one, all of them is line this direction, right? All of them line this like this, right? So you see that this is the x minus a2, x minus a3, and so on and so forth. All these actually 0 at a2. Everybody see that? The only is actually non-zero at a2 is what? Which one? In that term, in that sum. The only term that actually non-zero is what? Of course, h is non-zero, okay? And h cannot be 0 at h2. What else that is non-zero at when I evaluate when x equal to a2? I need the answer from you. I want it to be interactive, right? I don't want me just talking alone. Boring. I'm waiting for you. So let me repeat, right? So this is the first function, right? We'll do this one function. When I evaluate at a2, this is 0, right? You see that now the rest, all of these, all of them actually look like this, right? All of them 0 except one term. Which one? Hmm? I equal to 1. That's correct, right? Because x minus a2, this is x minus a2, right? X minus a2, x minus a3. All of them 0 here, right? Because this is a function. The only one is actually here. I do it yesterday. This is x minus a1. So it's 0 here, but it's, of course, non-zero here. Everybody see that? That's correct. Very good. So we have only one. The first term is non-zero. So that is exactly what we have here. C1, right? A2 minus, this is x. X minus A1, A2 minus A1 plus H equal to Z2. Okay, so we do the same. We do the same thing. So we do the same thing, right? How about for AJ? Let's say, how about A3? Maybe do A3 first. Let us work together. How about A3? How many terms is non-zero? Is this 0 or non-zero? Or A3? When x equal to A3, what is it equal to? 0 or non-zero? 0, that's correct. How many of them are actually non-zero here? How many? 2 or 3? Okay, 2. Some say, so most of you say 2. Any say 3? No. Okay, that's right. That's 2, right? Because when you are here, right? When you are here, on the x minus a3 and then x minus a4 are going to be 0. The only one actually non-zero, x minus a2, right? And then x minus a1 is non-zero there. So only 2. So now we do generalization, right? Do generalization. How about at I equal to j? How many terms is that are non-zero? J minus 1. That's correct. Very good. So that's exactly what we have here, right? Exactly j minus 1, right? At x equal to aj, we have j minus 1, non-zero. And of course, h is non-zero. The first one is 0. Okay, finally, we get to the am, of course, right? J equal to m, m minus 1, m minus 1. So we have this. Okay, so we have m equations. We have 2 more equations that we need the slope on the left. The slope on the left, when x less than a1, right? When you take the derivative, the slope on the left. Okay, let me go back here, right? On the slope on this guy, on the left, that means here, right? On this side, the slope on the functions. This is x minus a1, x minus a2, x minus a3. The slope is 0. Everybody see that? Because the function itself is 0. So the only slope that is non-zero is this one. Everybody see that? H is constant, so the derivative is also 0. Okay, so what we have is the derivative of this times c0. That is the slope of f. So, and the derivative is actually negative, right? Negative 1 because we know the rule, right? The derivative of this with respect to x is negative 1. This, right? This is negative 1. So times c0. So negative 1 times c0 is the slope when x is less than x1. And it must be equal to SL. And SL is the slope on the left of the original functions, which is given to us, right? So let me actually explicitly say so. So this is, we have SL here. And then we have this one, the S right. So they are given to us. And same thing, similarly, right? So we're gonna take the slope on the right. Okay, so tell me, what is the slope of this? So the slope of this at x equal, let's say this is a. I'm thinking about this is am, everybody, right? This is let's say m equal to 3. Let's say m equal to 3, right? This is the last one, right? This is the last one. We want to consider the slope on this side, right? Okay, so what is the slope of this one when I evaluate x? Let me repeat, right? Now we want to evaluate the slope of f when x greater than am, right? When x greater than am. What is the slope of this when x greater than am? 0. Why, right? Because here, this is a function. It's 0 everywhere, right? Of course, it's 0 here as well. So this guy have no slope on the end point. Okay, and this is more interesting. How many of them actually have, what is actually have any of them actually have 0 slope on this side? Any of them? Any of them has 0 slope? Or you can either tell me which there's an m term here. Of course, this has 0 slope either, right? This has 0 slope. We convinced, right? The question is how many of this sigma rectilinear function here have non-zero slope when x greater than am? How many of them? M, right? All of them have non-zero. But this guy, right, have non-zero. Actually, the slope is 1. This one slope is 1. Everybody, even AM here, right? The slope is non-zero. Good, very good. So we have all of them. And each of them, actually, the slope is 1, right? Because rectilinear functions. I don't know why it actually is, it sounds weird. I'm very far away from my phone, so we cannot blame my phone. Um, okay, so maybe the battery could be? Battery, ran out of battery? See that even, I don't say it still sound very, uh, maybe, but I don't know. Hello? Yeah, maybe better. Maybe, yeah, maybe better. Okay, so it's good. It's good. So we have m equation, m unknowns, right? And are these is this system nonlinear or linear system equation for these coefficients? I'm asking not difficult question. Linear or nonlinear? Linear. You see that everybody, you see that on the coefficient itself even appear linearly, right? We don't even need to look this equation because we know that on the coefficient appear linearly, right? If this is equal to something m, then must be linear system equations of m plus 2 unknowns. Okay, good. So we can put them into matrix form, right? And you look at it, actually it's a lower diagonal matrix, right? I'm sorry, lower triangular matrix. So it is very to solve. How do you solve this lower triangle matrix just for fun? Asking for fun. Huh? Sorry? Well, that's too complicated, too advanced. You are so advanced. Simple. Huh? Forward of substitution, that's fair, that's good, right? That's for good. This is that you solve this, right? Or you actually um, um, yeah, yeah, actually, that's good. The force, right? You solve for this first, and then when you have that, you substitute here, you solve for the second one, right? So this is a forward substitution. So remember Gaussian elimination, LU factorization, right? You do forwards, actually, typically you do forward elimination and then backward substitution. So that's why when you say forward substitution, I'm a little bit hesitation, but yeah, in this case, yes, you are right. So we forward substitution, right? It's very simple. You can solve it explicitly that way. Okay, so you see that, right? So what we have shown that we can represent any piecewise linear function exactly with a neural network. Actually, let me actually plot the neural network for you as well. So this is the neural network. Actually, I'm sorry, I shouldn't do this. Let me redo it. Okay, so that is we have shown, right? We have shown that we can find C0, C on the Ci and H such that we can represent any piecewise linear function exactly. And if you want to put them into a network, this is how the network look like, right? Look at this, it's actually very easy here. The input is X, right? The input is X. You multiply by weight -1, you see here, right? That's our first neuron. The bias is A1. That's our first neuron. The second neuron, of course, this. We have actually m plus 2 neuron here. The second neuron is what? X times the weight 1 minus A1. Everybody see that? And on the way to the last term in here. So we have m neurons here as well. So we have total m plus 2 neurons from X into there. Good? So far, so good? And then after that, we just see that's a linear combination, right? So C0, the weight for, because the output of this neuron become an input for the output neuron, right? So they're going to be C0 times sigma times the activation function here. The output of this one is activation function on this, right? So C0 times this, which is here, and then C1 times this, and on the way Cm times this. So on the weights, right? So remember that we do R phi transformation of the output of the previous layer, right? So R phi, right, combination of the output. In this case, the input is there's no output, right? And then add the bias. Of course, that's R phi, and then act the linear function, and we do it again. The output here, we do R phi transformation, and then we do activation functions. In this case, we don't only need to do R phi, right? This is R phi. R phi, the whole thing is R phi transformation. C0 sigma A1 minus X, C1 times sigma X minus A1, and so on and so forth. This is the first two. Everybody okay with that? And then the bias is H. What is activation function for the output layer? Because remember that we only do R phi transformation and then nonlinear activation function, or in general, just activation function. What is the activation function for the output layer? Because we want to represent that function exactly. What is the activation function? Actually, very simple question. What's that? Somebody say something? Identity, one. Identity, right? Because you don't do anything, right? You see that after do linear R pi decomposition of on the output of these neurons, and then plus a bias, that's it. You don't need to add anything. That's a identity activation function. That's the output. Everybody see that? Any question? Are you okay? You look puzzled. Any question? Are you sure you're okay? You sure? Everybody okay? Any question? Because if you miss that, you miss the this is important. We spent how many? We spent half an hour today. We spent some time yesterday, I don't know, or 2 days ago, half an hour again. It's important because I do very slowly to make sure that you understand. And if you don't, you need to let me know now. Because actually I can look into your eyes, I can know whether you don't or you're not. Some of you looks very confusing. Some of you look very comfortable. Are you okay? Are you sure? And some of you just don't want to look at me. Worrying that I'm gonna call you, right? All right. I understand. I used to be like that, so it's normal. It's normal. But the key is that don't worry. I'm your friend. I'm not your professor. He is. I'm not. I'm a visitor, right? I've been here for 2 weeks and I'm gone. So I'm not that scary like him. Okay, so I'm sure. Can we move forward? Any question? Are you sure? Don't worry. Just ask me if you have question now. Because if you miss this, that is actually we spend like an hour. Actually, it's just a waste, right? If you don't understand, I really want to make sure that you understand before we move on. Are you sure? Yes. Good. Mm. Okay. Yeah. So notice, right? Notice that. Okay. First, we don't design this. So let me actually answer your question differently, right? We actually start from a mathematical, completely mathematical point of view. We never design any network up so far, right? Our question is very simple. Our question is very simple. If I have a piecewise linear function, right, can I find a linear combination of ReLU activation function such that I can represent that piecewise linear function exactly purely from math point of view, no computation, no neural network up to this point. The only thing that connecting with neural network is that I'm interested in this particular function. I want to find a linear combination of this particular function, right? It just happened to be, but no one, actually, this function is actually very popular in mathematics as well, by the way, everybody. This actually function, right? It's just the computer science people call it a rectilinear function. But in mathematics, there are many ways to call it. In fact, if you do more math later, you see this function pops up everywhere, right? Basically, you just keep the positive part, remove or set the negative values as zero, right? So if you do more math later, you see this function is almost like everywhere, right? It's actually very popular in mathematics. We just simply use the terminology of computer science here, right? So let me make it clear. We are interested in this very weird functions, right? And we look and it itself is a piecewise linear. And we ask ourselves questions. If I have a generic piecewise linear function, can I find a linear combination of this special function that can represent that generic piecewise linear function exactly? Purely math point of view, no computer science, no neural network here at all. And we have trying to answer that. Now, after we answered that, I said, okay. Can we put this into a neural network or not? Right? And that's what we're trying to do. Actually, we can roll it out as a neural network. This is the same as this neural network. So it's after the fact, right? Not before. We don't design a neural network to represent. We actually find a linear combination of that particular function to represent the piecewise linear function exactly. And then we ask ourselves, can we design a neural network that represent that linear combination exactly? And we have spent about 5 minutes to say, yes, that is the same as this neural network, right? So this is actually fully connected. It's just like one input, many neurons in the middle, and then one output. And this is not uncommon. If you have scalar functions, then your output would be one, right? And if you are in one dimension, right, then the input is only one, right? So, and of course, if you work with multiple input in high dimension and multiple output, right, then you have there's going to be a vectors, right? But this is not uncommon. Okay, the second part to your question is that why there's no activation function here? Because depends. For our case, we don't need any activation here. You can think two ways. We don't need any activation function, or we need the simplest activation function, which is identity, right? We don't need nonlinear activation function to represent that function exactly. But if you want to be fancy, you want to put a nonlinear here, then you cannot represent that function exactly, right? Okay. So does that answer your question? Yeah. So we don't design. We just start from math, and then we try to see, oh, can we represent that as a neural network? And the answer is yes, we can. Okay. Okay. Very good. Actually, that question is very, very good. Any other questions? Please don't hesitate to ask me a question. Okay. This is your chance, at least for 2 weeks. Okay. Or we design. Okay, so you can think of this way. We actually have constructively construct or systematically construct a neural network that can represent any piecewise linear function exactly from mathematical point of view, right? So that's another way to think about it. The activation is still ReLU. We don't use different activation function. The only way is that we don't actually just put into the any like TensorFlow or PyTorch or JAX to find the network for us. We use simple math to systematically explicitly construct a new network that can represent any piecewise linear function exactly, just purely from a math point of view. Okay. All right. Very good. Any other question or clarification? If you want to clarify anything, that's very good questions. Please keep asking questions. That's important. So it's interesting, right? If you are in the US, you take the class, you have 1,000 questions. People ask all kinds of questions. When you go to Asia, you have no question. We should ask more questions. That's good. Asking question doesn't mean that we don't understand, right? It's just asking questions is more interaction that you keep me awake, you keep yourself awake, and also, clarification is important. Okay, we continue our math journey, right? Math journeys. So I'm going to look at a very special function in mathematics. It's called half functions. This is if you do interpolations. Any of you actually learned interpolation before? Or Lagrange interpolation, made the famous interpolation, but has Lagrange interpolations. Any of you does not know Lagrange interpolation? So actually that question was not good, because when I say does not know, nobody is going to say yes, they raise hand, because that's so that I don't know, right? And typically we Asian, we don't want to say I don't know. We say I want to know everything. I know everything instead of I don't know. Okay, okay, don't worry. I just joking here, right? Lagrange interpolation. Any of you are not familiar with you? You have a question? That other way. Okay. Yeah. Okay. So you must be Marco. Yeah, because I look at the list, you have an Italian name, I think, maybe, and you are the only one who look like Italian to me. Okay. So yeah, so the Lagrange interpolation, I hope everybody know. If not, please raise your hand. I can review that to you as well. But interpolations, I suppose that you know what linear, at least this is linear interpolation, right? So I'm going to look at a very special function here, which is called, this is if you do finite element methods in particular, right? There's a special name for this. What's the name for this? Hat function, right? Like hat, right? If you go to Vietnam, I'm originally from Vietnam. If you go to Vietnam, you see like women wearing this hat a lot, right? This hat. And you go to China, some China also have that kind of hat as well. But this is like the traditional Vietnamese hat for women. Actually, it's very useful, especially we are in Asia. It's very sunny, right? That hat's actually very useful, especially if you work in the farm. So this is the name is very intuitive, right? So it's a hat function because it looks like hat. So what is this hat function special thing? It's one here, right? And then it's support. It's zero everywhere. Actually, I should put here it's zero everywhere, except within its support. The height is one, and then linear both sides. Okay. So if you look at these half functions, it's a piecewise linear. Everybody see that? Zero, linear, linear, zero, right? So you can immediately write down what G look like, this half function look like. Zero everywhere, but have a negative slope on this side. Oh, so I'm sorry, negative slope on this side and positive slope on this side, right? Good. That's it, right? So where H1 is this, H2 is this. And this is just a special case, right? Remember that we can do any piecewise linear function, any piecewise linear functions. this is a very special piecewise linear functions. So then you immediately can see that this can be represented exactly by the linear combination of actually only, I'm sorry, there's a sigma here. There's a mistake here, right? Sigma. You can represent by three ReLU activation function, linear combinations. And we only show that, right? This is mistake here, sigma a 3 minus x. Okay, so yeah, by just doing the some of you say by forward substitution, right? You can actually see that you can solve for the coefficient like C0 here, right? And what is that there? A1. Okay, so how about this? I'm confused myself. Maybe I make more mistake. You can you show it? Okay, so can you do the homework and check this for me? How about this? Okay, I'm gonna ask you later. Next time, I'm asking you. This is homework for you to check my result here is correct or not. Okay, but in any case, we can just represent by three linear combination of three ReLU activation function, which we already convinced by the last slide, right? So that's fine. So we can represent each of the half function exactly. Okay. So that is good. Now we can we are already in the position. We are in the position, right, to show that ReLU neural network is actually universals, and we do so in two steps. And when it is universal, you means that this is what you mean by universality, right? This is just a computer science way of saying the same thing in mathematics. Basically, we say that the collections of all one hidden layer ReLU neural networks is dense in the space of continuous function between on about it or compact subset, right, of R. In other words, right, this is the space. Let me actually write down here for those who are actually not familiar with. Let me actually write down here. So C of AB is a collection of all functions, right, continuous on AB. This is space of all continuous function, all the space on continuous function on compact set AB, right? Bounded compact. I'm sorry. So so let me actually check just for fun. In Rn or in R, compact means what? Have you heard compact set? What the compact set mean in Rn? Just for fun. Say again. That's correct. That's very good. Very good. Actually, I like it. Many of you answer the question, yes, close and bounded. That's right, correct. But it's not true. It's not true in infinite dimension, okay? Only in Rn, close and bounded. And this is we are in R1, right? So when you look at the literature, people talking about your continuous function on compact set. So this is a special compact, right? In one dimension. Okay, very good. I like that. Okay, so what we're going to show is that the collections of all one hidden layer ReLU neural network is actually dense in the space of continuous function on AB, right? And that in the computer science language is a universal. Universality is nothing more than density from mathematical point of view. Okay, and we want to, in other words, and another way to actually think about is that if you give me any function, from the space any continuous functions. And if you give me any desired accuracy, epsilon, I'm going to show you I can always find a neural network that actually can approximate your function in the desired accuracy that you want. That is another way to say density or universal in a more constructive way, right? Density means, or universal means that you can approximate anything in any desired accuracy that you want. That means density, okay? Or universal. So we're gonna do in 2 steps. We're gonna show that any continuous function can be approximately well by piecewise linear function in any desired accuracy. Okay, so you have a continuous functions, and you can show that, oh, you give me a continuous function and you give me an epsilon, I can find a piecewise linear function that can approximate your continuous function in that epsilon. That's the first step. And then we know that that piecewise linear function, piecewise linear function can be represented exactly by a Relu neural network. We're done. That means a Relu neural network can approximate your continuous function in any desired accuracy. Everybody see the big picture? Okay, let me repeat the big pictures. The big pictures, we do 2 steps. The second step is obvious. We already did the second step. The first step is to show that any continuous function can be approximated well in any desired accuracy by at least one piecewise linear functions. That's what we're going to try to show. And if we can show that, we are done, because any piecewise linear functions can be represented exactly by a Relu neural network, which we have shown. Then, in other words, any continuous function can be approximately well by a Relu neural network. Okay? Any question by that's the roadmap that we have. Okay. How about this? Let actually us take a break right now until 11. So we so that we don't have a discontinuity. Okay. I see you at 11. Okay. So the next hour is going to be more on mathematics, right? But it's just simple math. I promise you, going to be very simple mathematics. So that is the 2 steps that we're going to try to do. So we're going to look at this, right? So we're going to look at the special half function here. With special half function, you see that I'm looking at an interval, AB, right? I'm going to subdivide my interval into m plus 2 point, right? From x0, x1, x2, so on and so forth to xm plus 1. Okay, so we have total m plus 2 points, and therefore we have m plus 1 intervals. It doesn't need to be uniform, right? And can be different. And on each point, on the interior, on the left point here, I'm going to have this piecewise linear functions, 0 everywhere in the rest of the interval, but they have slope, it's a negative slope here. So this is the first, like, half of the half function, half of the hat function, okay? And on this end, because I don't have any support outside, right? So I only take the half on the endpoints. I also have the other half of hat functions with the positive slope point. Everybody okay with these 2 special functions at 2 endpoints? Just a linear function? And then in any interior points, I actually truly have a full half function, right? With the support between xi plus minus 1 and xi plus 1. Okay, so these are the one that we just constructed from the last slide. Okay, so that is our interval, and that is just the set. And notice that on the height, right, on the height of the half function is 1 on purpose. You see that I divide by appropriate By the way, where's H? Did I define what HI means? Okay, I haven't defined HI mean. All right, so let us make sure that we define that. So HI is equal to HI plus 1 minus HI. Okay, so that is nothing more than the length of the. So for example, right, this is H. This is HI, right? The length of or the distance between xi plus 1 and xi. That's it. Right? If I take xi minus, for example, I take xi plus 1 minus x, this is the slope, I divide by this, right? Then I want to make sure, I will make sure that the at x equal to x1, right? This become h1, hi, right? So hi divided by hi is 1. This is 1. So that's how we ensure that all the half function have height equal to 1. Just for simplicity, we don't have to do so, but just for simplicity, okay? Any question on this layout of half function? Yes? Oh yeah, sure. Yeah. So we looked at the Relu neural network from finite element point of view. I don't want to go into deep because not everybody know finite elements, right? But I just want to make a connection so to actually to prove to you that we look from the finite element point of view, right? Or from a traditional math point of view. But yes, you're right. So this is actually truly finite element per way of looking thing. But fundamentally, it's just linear interpolation that you're gonna see, right? You're gonna see linear interpolations. We organize the linear interpolation in special manners. Okay, so we're gonna look at. Okay, so let me tell you what we have in this figure here. So this is the true function, the true continuous function, right? The dash curve is the true function that we are interested in on that interval, right? From x0 to xn plus 1. Okay. So we're gonna try to put down linear interpolations using half functions for that particular functions. Okay. So how do we define the linear interpolations on each subinterval? So I think, yeah, I do a little bit mess up in terms of notation here. Okay, I do a little bit mess up in terms of notation here. I should have seen that until now. Okay, so by our previous so this figure is actually does not is not good. That's not is not good, right? We recall that the I, which is the interval I, is between xi and xi plus 1. So what we show there is actually not the correct, right? So this should be I minus 1. This is I minus 1. Okay, so that should be I minus 1 instead of I. So we're gonna look at I minus 1 so that you can see, and then we generalize to I. Okay. What you're gonna see is that this is the phi I. This is a half function on the I, right? This is the half function that we just construct from last slide. We just define phi I this way, right? Oh yeah, I should have to. You have to tell me. You have asked me the question already. This is I is nothing more than defined as the interval between xi and xi plus 1. So phi I is actually a half function at xi. All right. So you see that if I look at the I plus 1, I plus I minus 1, I'm sorry, interval, which is this interval, the two half function that this half function and this half functions have two non-zero part, right? This non-zero and this non-zero part. Okay, so that's the non-zero part. And we're gonna define a linear interpolation. We're gonna define a linear interpolation. Actually, let me write down. You know, write down here. The linear interpolation where do we have enough space? Okay, we're gonna write up here. I mean, which colors? Let me do maybe yeah, purple color is okay. This is green, right? Okay, good. Let's do green. So the interpolations. The capital I stand for interpolations. H because the size, right? The size depends on H, and you know, one here means linear interpolation. Okay, so one here means linear interpolation. Just remind us this is linear interpolation. A little bit too much of notation here, and our function is v. This original function is vx, and then let me put down here. This is vx. Oh yeah, right here. We actually put it here, vx here, right? This is our exact function is vx, and we're gonna define the interpolation of v on interval I minus one. Okay, a little bit of a lot of notation here, but each of them have a meaning. Okay, so what we do is that we're gonna do so. This is so how do we define the linear interpolations? And actually, it's quite easy, right? Because this line, this is a linear interpolation. Everybody see that? Of the function, the orange dashed line. You just simply connect these 2 points by a straight line. That's a linear interpolation. Everybody agree with me on that? The only question that we're gonna need to answer is that how do I write this green as a combination of the blue and pink? Right? Remember that the blue is a non-zero part of Phi, and the pink is a non-zero part of the Phi minus one, which of course I can't, right? Because I should be able to do so, right? So that's what we're trying to do, and actually it's quite easy to do so, and we actually this is what I wrote for the generic one, but I'm gonna just write it down for you right now. So it's gonna be one over h I minus one xi minus x v xi minus one plus 1 over hi x minus x I minus 1 v xi. Okay, let's check. Let's check to see. Of course, let's check. I'm just write this. Actually, I'm trying to write this. Actually, I'm going to try to write this this green. I haven't done anything yet. Just the green. The green. How do I write the equation for the green? That is the equation for green. So first, we need to check: is it linear in x? What I just wrote, because this is supposed to be linear, right? This is linear in x. That's correct, linear, right? Because v xi minus 1, xi minus 1, xi are given. So v xi minus 1 and vx are given number. They just numbers. So it's a linear in terms of x. So that's a good side. Second, we need to make sure that actually linear functions, right? How many information is enough to determine a linear function in 1D? I'm asking middle school class question. How many information is enough to determine a line? A line. Two, right? Two information, either 2 point or a slope and a 1 point, right? Or whatever, right? Just two information is enough. So we need to check. So we know that this is linear, and we need to check whether it's matched the 2 point. That's enough. Right? Linear and match the 2 point, and they're unique. There's only one unique linear function passing through 2 points. So I need to check the 2 point, and I'm done, right? So let's actually check. When x equal to xi minus 1, x equal to xi minus 1, this is equal to what? That term is equal to what? When x equal to xi minus 1, because we want to check whether the new thing, the thing that I wrote here, I claim, right? I claim that this is the green. So in order to verify that claim, I just need to check whether that actually matched at these 2 points, and I'm done. Right? So first, let's do the xi minus 1 first. And when x equal to xi minus 1, what happened to this one? 0. So on the only thing is this one that I need to care about. So this becomes xi minus 1, right? And but divide by hi minus 1. So xi minus 1 is exactly the hi minus 1, right? By definition, we define. Where did I define? Actually, in the previous slide, right? In the previous slide, we define, let's see, hi is equal to hi plus 1 minus I. So this, when you rewrite minus 1 here, this become I, this become minus 1, right? So this is equal to 1 when I evaluate that at x equal to I minus 1. So 1 times vxi minus 1, exactly this. So it match the green at I minus 1. And same thing, it match the green line at I, right? By substitute x equal to I. When you sub x equal to xi, this is 0, and this become bxi. Same thing. Everybody see that? So we are sure that whatever I just define here, this, what I define here is a linear, and it's exactly the green. Okay. So that's for I minus 1, and this is just, I wrote it into your I, right? So this is a linear interpolation of V on the I interval. That is on the I minus 1. This is just generic, right? You just replace it. Okay, so good. Now, what you notice is that this xi minus 1 minus x over hi, right? This is nothing more than this guy. I'm sorry, than this guy, right? So I just simply replace by phi x here. 1 over hi xi minus plus 1 minus x, right, is nothing more than phi, because our definition of phi, right, on this part of phi, is 1 over hi xi minus 1 minus x. Everybody okay? So I simply replace this with phi, and I replace this with phi plus 1. Good? Okay, by definitions. Okay, let me repeat, right? There was a mismatch on my slide here. I'm sorry, right? There was a mismatch. So we start with I minus 1, and then we just rewrite it as an I. And then after that, we realize, oh, this is nothing more than phi. This is nothing more than phi plus 1. So I just put it in here. Good. So we actually have to convert. In other words, right? In other words, We start from a very simple linear interpolation, which require no knowledge about anything. We have just written the linear interpolation in term of half function that we introduce. Okay, now we're gonna see the error between our interpolation and the original functions. This is our interpolations, and then this is our original functions. And we're gonna look at on the interval, right? II here. Okay, so remember that IH1V on the interval I is VI V XI, VI plus 1, VXI plus 1. So let's check on that. So okay, here you see that VI VI plus 1 XI plus 1. That is our IH1. That's the interpolation. So it's so interesting that this turned into this. Right? It sounds like weird or interesting. But you also notice, actually, it's very easy. You see, right? If you look at these two functions here, if you look at the two function, half function that set the same point, at any point, the pink plus the blue is equal to what? At any point inside this interval, where the blue and the pink share, right? At any point here, the pink value is here, right? The blue value is here. What is the addition? So if I sum them up, it is equal to what? At any point, doesn't matter. At any point, the sum of the pink and the blue is equal to 1. It's very easy, right? But it's equal to 1. Everybody see that? So that's the interesting property of the half function. You add them up, VI plus 1 equal to 1 when they share on the interval that they are both non-zero. They are adding up to 0 to 1. Everybody see that? Are you okay? Are you sure? Right? The pink, regardless of where you are, the pink plus the blue is equal to 1. And it's also obvious, right? Because you see that they try to approximate this constant function here. Okay, so that's the trick that we use. We replace 1. This is 1 by Pi plus 1 for free, because they are equal to 1. The sum is equal to 1. The reason we want to do so because we want to combine with these. Everybody see that? This is equal to this. I don't do anything. The only trick that we do is that we replace number 1 by Pi plus 1. A trick. Is it good, everybody? Are you sure? Now I'm gonna combine. I see Phi here. I see Phi here. I'm gonna factor Phi out. So we have Vx minus Vxi. Agree? And then Phi plus 1, I factor it out. I have Vx minus Vxi plus 1. Good? Are you okay so far? Okay. Okay. Now notice this is equal to 1, right? At most equal to 1. This is at most equal to 1. The only thing that we don't know is this. Remember, Vx is up to this point V. We don't know Vx. We only know V at the points, right? We don't know V anything else, right? So if we can bound these terms, and these actually similar nature, right? You see that Vx minus Vxi minus 1, Vx minus Vxi. If we can bound each of the term, right, we are done. That is the statement that I wrote here. But in order to do that, we have one definition that we need to deal with, right? because this is the very popular definition of how to measure the uniformity of the continuity of a function. So you know what continuous function, right? So you know the notion of continuous function. Are you also familiar with uniform continuous function, right? Okay, so some of you say nod your head. So modulus of continuity is a way to measure how uniform your continuous function is. Okay, so the definition is the following: for any f in the space, any f that is continuous, the modulus of continuity is defined as this. You evaluate fx at 2 points. Of course, you need to pick. So this is the modulus of continuity depends on two things. It depends on the functions that you have, and it depends on the interval that you pick. Okay. Okay. So when you look at the function and when you pick the interval, then the modulus of continuity defined this way. You take f evaluated at any 2 points that is within that interval. So this 2 point can be different, right? And remember that x and y is over the whole interval. As soon as x and y is within h, but it can be anywhere, right? It can be anywhere as soon as it's less than h. And you evaluate your function at these 2 points. You take the absolute value, okay, and then you find the supremum, or the maximum is not really the maximum, right? The supremum, or I mean, in an easy way, the largest, right? And in the easy way, or the smallest upper bound. The supremum. Are you familiar with supremum? Are you familiar with supremum? Okay, if you're not familiar, then you know, for the moment, forget about this. Just a maximum. It's not true. It's not true, right? You can you know, to understand the concept, just put the maximum here. Maximum. You look at 2 points, any 2 points that actually in between your interval here, and take the difference and find the maximum difference. That's the measure of the modulus of continuity of your functions. Okay, so that's the modulus. You can show that for any continuous functions, the modulus of continuity is a continuous function from the right. That means when h go to 0 from the right, right? Then the limit, the modulus of continuity actually approaches 0 for any continuous function. Okay. So that's what I mean, the modulus of continuity. Okay. So it's just the maximum variations or jump. Think about that of the interval of the function itself within the interval that you're interested in. Okay. So you see that if you change h, right, or you change the functions, this is going to change. Okay. Now, using that definition, we can continue, right? Notice actually one more thing is that on the half function, everybody on the half function is non-negative, right? Because half function by definition is non-negative. It's 1 and then down to 0 and then 0. So non-negative. So we're gonna use symbol triangle inequality. Remember that Vx minus this is equal, without the absolute value, this is equal to, in the last slide, right? In the last slide, it's equal to this. So now I'm going to take the absolute value, triangle inequality, right? I have this. Are you okay with that? Because notice that on the phi are positive. Okay. Now next. Now we use definition of modulus of continuity. Okay. Remember that we are, because x. Actually, let me go back here. We are interested in x in this interval, right? And we see how far our interpolation compared to the original function within this interval. So x is in between xi and xi plus 1. Okay. Now, so we're gonna do a couple of things. We're gonna do actually I should use the correct h. That is not the h, should be hi. Okay, so everybody, so this is generic, but from now on, okay, so from now on, I should put here from now on. We assume that on the hi are the same. So we have a uniform on hi is equal to h, right, for all I. So that means uniform discretization. If you are familiar with otherwise you don't have to worry about that, right? It's just uniform. That means on the xi, from xi to xi minus plus 1 is h. Every interval is h. Maybe here, right? Everybody here, h. What we do here is generic, but for simplicity, we're gonna do h just for simplicity. Okay. So if we assume that is actually everybody is h, right? Then we, because x is in the interval, right? X is in I, right? So the maximum difference between x and xi cannot be bigger than h. That's the first thing that we need to know, right? Because we are within that interval. Therefore, the difference between Vx and Vxi cannot be greater than the modulus of continuity, right? Because the modulus of continuity by definition is the largest, by the largest. Everybody okay? The modulus of continuity is the largest. So each of these, this is less than a modulus of the continuity WVH, right? This is also less than the modulus of continuity VH as well, because x minus xi plus 1, right, cannot be larger than h. So by definition of modulus of continuity, right, this cannot be larger than modulus of continuity, because modulus of continuity is the largest variations. So by doing that, I can replace both of this by modulus of continuity, right? This by W VH, this by WVH, and then I factor them out, right? So we have Phi WVH, Phi plus 1 WVH. I factor it out. Everybody okay? So this is what I have here. And what is it here? Phi plus 1 is equal to what? Some of you say like this, right? 1, like I mentioned previously. So this is equal to 1. So we actually had WVH. So very nice, right? So very nice. So what we have shown is that the error, the interpolation error, right? And now, and then remember, right? Remember this is for x in an arbitrary xi, right? For any interval, it is less than VH. And remember that this does not depend on any interval. We are within an interval right now, right? And we are less than the modulus of continuity h, but h itself does not depend on interval. So we conclude that regardless where you are, right? The difference between your original function and your interpolation cannot be bigger than the modulus of continuity. One, you determine the h. Everybody okay with that? So we start with a particular interval, but then our conclusion is generic for any points on the original big interval, because this does not depend on the interval itself, right? It's only depend on the function and the size of the little interval that we pick. Okay, so any questions so far? Any questions? You sure it's okay? Very simple, right? Okay, so we have this. Let us continue. So we see that the interpolations, linear interpolation, and or this, right? So you see that I can do a linear interpolation between any point, linear interpolation. So the linear interpolations, the error between the linear interpolation and the original functions is bounded by the modulus of continuity, which is good. Now remember that we say that each of h is equal to hi, on hi is equal to each other's, right? In fact, actually, why don't I ask you to do this, right? I say this. Okay, so from now on, we assume this, but actually there's two things. Or, because it sounds like restricted, right? Restricted, that the way that we derive, the way that we derive, the way that we derive up to here. So this is for, let me write out here, for two cases, for the first case, when on the hi is equal to h, or b, the hi does not need to be each other's, right? This sounds like, oh, it sounds like very restricted. On the hi need to be equal to h. But then in fact, this result does not need to be satisfied for the uniform case. It can be also uniform for on hi that are different, but one condition. What is it? I can replace hi equal to h with what? I don't need it to be equal. Somebody say something? Less than. That's correct. As soon as on the that's correct for on I. As soon as basically you pick the largest interval, right? And we call it h. As soon as on the subinterval, right, less than h, then this is still true. By definition, the modulus of continuity. Okay, by the definition of modulus of continuity, check on that. Okay, so this is the first case is clear, but the second case require you to think about the modulus of continuity. Homework, think about it. So it's not a restricted condition. Okay, it's actually generic. As soon as on the interval is less than h, then it's still true. All right, so now we just, for simplicity, we're going to look at case A instead of B, right? So we have two cases, either case, this is true. So we're going to do what? Case A. Case A where on the interval are the same, right? And the size, because the endpoint is B and the other one is A, right? And remember that we have m plus 1 intervals. So H would be B minus A over n plus 1. Everybody okay with that? That's H, right? Okay, so instead of writing H, I write B minus A n plus 1. That's it. Okay, so I just rewrite that results with that. Now, look at this, right? Now, when I take, now I'm gonna pass to the limits where I have many little points. When the number of points go to infinity, and therefore h, right? When n go to infinity, h go to 0, right? Then this go to what? and this go to what? 0, right? And then this go to 0 as well because of the modulus of continuity. Actually, I put the green here. Here. So this is where you need to check, because you need to spend some time thinking about this and then convince yourself this is true. Okay? Then you see that when this guy go to 0, then the module of continuity is 0 for any continuous function. This is important for any continuous functions. And we are looking at continuous function right now. So if we pass to the limit when n go to infinity, that means h go to 0, right? Then the upper bound, which is the right hand side, the upper bound of the error between our original functions, our original continuous function, and the linear interpolations is actually 0, right? So what it says is that you can make, right? You can make this as close as possible to v as soon as we do what? We can make our linear interpolation as close as possible to the original function as long as we take as many points, or as long as we decrease the size of x sufficiently small. This result say that, right? This result say many things, right? This result say many things, but one of the easy thing to think about this is that, oh, if you give me an any epsilon, right, I can always find sufficiently small h or sufficiently large number of points such that my linear interpolation is within that epsilon compared to your original functions because of this result, because the limit is 0. Everybody understand that? Okay. So that's actually quite achieved, right? Which means, okay, this is the limits go to 0. So we actually we have a few more minutes. So let me actually rephrase what I just said to you. Okay, so what we just said is really important because that's actually the universality that we are looking for, right? Because this is a continuous functions. This is a linear interpolations. This is purely mathematical thing that we just do. Very simple, actually not even high advanced mathematics. It's just very simple math. We show that if you give me any continuous functions, right, I can always find a linear interpolations such that that linear interpolation is as close as possible to the original function in any desired accuracy that I want, because this is equal to 0, limit equal to 0. I just simply take more points. I should simply decrease the size of my interval. Everybody okay? But we know this is piecewise linear function, and piecewise linear function we only show that can be represented exactly by one hidden layer Relu neural network, right? Therefore, for any continuous functions, right, I can always find a Relu neural network, one hidden layer. I can actually exactly find what it is, right? We only showed that a few slides ago. Exactly how the structure or the architecture, like one of our classmates just asked, I can design exactly architecture of the Relu, one hidden Relu neural network that can approximate my function well in any desired accuracy, right? Because of this result. In particular, how many computational unit that I need for, or how many neurons that I need? How many neurons that I need? How many neurons that I need? Actually, there's a mistake on this slide. So if you read this slide, then the answer is wrong. How many? Actually, it's quite it can be true as well, right? How many units is necessary for me to to represent the function exactly. Yes. What's that? 2m plus 2? Well, that's a lot. No. Because remember that we have, remember, okay, let me go back here. Let me go back here. That's a lot. That's a lot. Oh, and this is in the order, you are right, right? But it's a lot more than we need. A lot more than we need. All right. Remember that we need for this one. Actually, let me go back here one more slide. So how many breakpoints we have? M breakpoints, right? If you have M breakpoints, and then you have two slope, right? If you have M breakpoint, two slope, then how many neurons that we need? We need M plus one neurons, right? M plus one neuron, M plus one neuron, M plus one neurons. Okay. So for our case here, where we have a function, continuous function on the bounded interval, right? How many points actually? How many points that we have here? I'm sorry, I go so fast here. Where is it? So we have m plus 2 point here, m plus 2 point here, right? Break point here. We don't have slope. We don't care about slope, right? We don't, because our function is not extended over the whole real line here. We have only up to this point. We have m plus 2 points, break points. M plus 2 break points. We have m plus 2 break points. Of course, you can extend this slope if you want. If you want to make things a little bit easier, you have to extend this slope here a little bit, right? Extend this slope. You can extend this slope. So you have m plus 2 break points and 2 slope at the end. So how many neurons do we need to represent the piecewise linear function with n plus 2 breakpoints? M plus 3, right? Remember that we have m breakpoint, then we have m plus 1. If we have m plus m breakpoint, then we have m plus 1. So we have m plus 2 breakpoint in this case, so we have n plus 3. Okay? So we need only m plus 3 neuron in order to represent, right? Which is exactly what we need here, right? M plus 3 neurons to represent this linear interpolation exactly. And the linear interpolation, on the other hand, approximate the functions in any design accuracy, right? Then we just do that, right? You just so you can do reversed, right? You give me a function, you give me an epsilon, that desired accuracy, I can find an n. Because of this result, I can find n. And as soon as I can find n, I can find exactly how the neural network look like. M plus 3 units. Okay. Okay, so I think we're gonna take a break for lunch, and then we're gonna look at a very special case, not only the continuous function, but Lipschitz continuous. Because so far the modulus of continuity sounds like, you know, a little bit too abstract for you, right? Or us. We're gonna look at the Lipschitz, which is a little bit a special class of continuous functions, and then we're gonna see exactly what the modulus continuity look like. Okay, so we're gonna do that after lunch. Okay, I see you everybody after lunch. I see you at lunch. Okay, so at 1 o'clock, let us start again. Any questions before we start? Yes, please. Say it again one more time. I'm sorry, I don't quite. Yeah, just slow. Just don't worry. Yeah. You mean which one? I just go slow. Stop me when. Stop here. Oh, this is not a Laurent function, right? This is just a half function right now. Exactly, exactly. Three, yeah, by three, actually three. We show that actually every half function is can be represent the linear combination of three half function. Yeah. Each Relu function can be no, don't worry. Just say. Just tell me. Yeah, yeah. Yeah, show me, and then I tell the class. Yeah.
If I have a general function from 0 to 1, and this slope is 1,
Huh?
and this particular value function we can write as a value function with the general value function of positive alignment.
Oh, okay. Okay.
So this giving me give us a motivation about we should choose this map between each layer to we should choose a map between each layer. That's only a linear map, but also but a map.
Family member.
A map.
A fine member.
Yes.
Yeah.
Okay.
Because any right. So what we have shown is that okay. So we do two things. Let me repeat this, right? This is important. So we have shown that any piecewise linear functions can be represented exactly by a linear combination of Relu. Okay. So this half function is a special piecewise linear. So therefore, it can be represented exactly by a linear combination of Relu, three Relu. You're okay with that? Okay. Now, what we have shown, is that okay. See, this is linear, right? So I'm gonna approximate this function with piecewise linear. So what we have shown that this linear can be represented exactly by the linear combination of half functions. Okay? Therefore, the whole piecewise linear approximation can be written as a linear combination of half functions. And the half function can be a linear combination of real dual. Therefore, a piecewise linear function, right? Again, just a piecewise linear function or the combination of half function can be represented by exactly right by the Relu neural network. Is that good? So what is the question that I still don't get the question? Okay. Any questions, clarifications? Okay. So we show, right? We show that. Okay. That, by the way, we go all the way here. We show that any continuous functions, right? Any continuous function can be approximated well, right? In any desired accuracy that we want using piecewise linear, right? Because of these results. And this result, you see, that's very simple. We just do a very simple math here. And because piecewise linear can be represented exactly by Relu neural network, one hidden layer in particular, that's what we show. Therefore, the conclusion is that the Relu right, can approximate any function design, any function, any continuous function in any design accuracy that we like, right? We just simply, right, increase the number of computational unit neurons, right? If you give me a tighter, right, tighter epsilon, I just need more neuron. That's it, right? So we're good. That's a universal approximation theorem for ReLU. So we see that is very, very simple. It's not that difficult. Okay, now I'm gonna, so far the, what we see is that this guy is how to be very abstract, right? If you haven't seen modulus of continuity, because it requires some little time to think about it, to build intuitions. If not, right, it's sound like this guy is so abstract to us, right? The modulus of continuity. But now if you assume further, if you restrict your function a little bit more, instead of continuous, we want a function to be Lipschitz continuous. So what is the definition of Lipschitz continuous? Actually, it's there. This is the definition of Lipschitz continuous function, right? And this is we're talking about global. I should have said this automatically means that global Lipschitz, right? So a function is Lipschitz continuous if you take me globally on the whole interval, right? If you give me any 2-point in this interval, and then right, it is 2-point interval, and then measure the function, the difference at these 2 points, and if this difference is less than and constant time the difference in x. So thinking about this, right? Thinking about intuition, think about functions like a box. If you have a function like a box here, actually let me do v so that you can see v function is box. The input is x, and the power output is of course vx. Okay, so this is input-output relations. If I give you two different input, right, and I know that the difference between two inputs is x and y. This is the variation in the input, and of course I have two different output, and I can measure the variation in the output as well. Okay. If a function is well behaved, the function is continuous, mean what? A small change in the input lead to a small change in the output. That's continuity means, right? Lipschitz continuous not only say a small change in the input lead to the small change in the output, but also the change in the output must be bounded, right, by a constant time the change in the input. That Lipschitz is require more. Everybody see that? Okay, so as you can see, right, as the change in the input go to 0, the change of the in output go to 0, right? So this Lipschitz continuous function automatically, Lipschitz continuous automatically imply continuous, but it actually have more, right? Because it say that the change in the output is actually bounded by the change in the input. That's what I mean by Lipschitz. Okay. And then if you want to use the definition, you see that the definitions of omega of v h. Remember that we do vx minus vy absolute values, right? And then we take the supremum for x minus y less than h, right? And x, y is in AB. Okay, so by definition of the modular continuity, the modulus is continuity is the supremum of this. So if you take the supremum both sides, right, you see that the modular continuity is less than L. Everybody see that? L times this. Okay, so because combining these two together, we see that WVH, right, is less than or equal to the supremum I think this is too low. Let me move to the other side. Combine these two together. We see that the modulus of continuity is less than or equal to the L supremum of x minus y, right? X minus y less than or equal to h, right? So that means, but the supremum, remember that if you haven't seen the supremum, this you can think about this as a max. Thinking about this as a maximum. So we want to say, what is the maximum of x minus y for all x minus y within h? What is it? H itself, right? So LH. So for Lipschitz continuity functions, the modulus of continuity can be explicitly written, right? Or bounded by L times H. So that's what we have the result here, right? By simply using the definition of Lipschitz continuity and definition of the modulus of continuity, we immediately get to the this fact. Everybody okay? Okay. So now we just replay the result. Remember that our results from last, right? Is this is less than modulus of continuity. For Lipschitz continuity, right? This we can replace this by L times H. L times H. And remember that this is H. Okay, so now things become much more explicit. And you see it's a linear conversion rate as well, right? You see that's actually very, very nice. Very nice. Very nice. So actually, let me stop here, right? So this is actually, this result is very explicit. Oh, I have a typo here. That's V here, miss V here, right? Interpolation of V. V minus linear interpolation is less than by the Lipschitz constant times B minus A n plus 1. And you see it's a linear conversion rate immediately. At n go to infinity, immediately you can also see that it's go to 0. And you just need to add more neurons, right? Any questions? Okay. If not, then we just move to this. So you said, okay, I want to construct so we would do one way. We'll ask the question the other way. I want my neural network to be within epsilon of my function. How many neurons do I need? That I can ask, right? So the result that I have showed to you is that if, right, you give me a function, and if I sufficiently have, as long as I have sufficiently large number of neurons, I can have the error very small. You turn the other way around and ask, now I want my error to be this much. I want to be my error to be about epsilon. How many neurons do I need? For example, in your practice, you want to construct your neural network to learn something, and you want your error, 10 to the negative 2, for example, right? You want 2-digit accuracy. And then you ask yourself, how many neurons that I should put in there to train my neural network, right? Now we're going to give the results on that, right? At least for ReLU. Okay, so that means we want the error. Remember, this is the error, right? L times H is the error. The upper bound is not the error. The upper bound the error. Because if the upper bound is this much, the error automatically that much as well. Everybody okay with that? This is the upper bound, right? If the upper bound is this, then everywhere is less than that. Okay, so if this is equal to about L, then just a simple manipulation, you see that n is about 1 over epsilon. So if you need your error around 10 to the negative 2, then how many neurons do you need approximately? I'm not asking a difficult question, huh? If you want error here to be 10 to the negative 2, then approximately how much n is? Any answer is actually correct. Any answer is correct. About 100, right? Because 1 over 10 to the negative 2 becomes 10 to the negative 2. It's about 100. That's it, right? If you want your error is about 10 to the negative 2, at least for RODU, one hidden layer, right? Before you even train, before you even design your neural network, and if you're really interested in one single layer, right, then you should pick about 100 neurons for that layer, more or less, right? Then you're gonna feel confident because this is the theoretical result that we can have. Everybody okay with that? So this is actually a very meaningful result, right? Not only it shows us the universal, but it's also tell us the way to design our neural network as well. At least, again, not generically true, right? Only for ReLU and for one single hidden layer, and also for Lipschitz continuous functions. Okay. So that's the at least give us intuition, right? As it gives intuitions. Of course, if you not have Lipschitz continuous, and if you have differentiable function, by the way, so Lipschitz is stronger than continuous, right? I just show you. Differentiable, how do you think about differentiable? Just testing on you, right? This is the math question, not no machine learning, no thing. Calculus questions, calculus. Differentiability is stronger or weaker than, we know this, right? So continuous imply differentiable, or differentiable imply continuous, or equivalent, just for fun. Differentiable imply continuous, that's correct. But continuous does not imply differentiable, right? So if some of you doubt, right? This is ReLU function. This is our ReLU function is continuous, but not differentiable right here, right? Okay, so ReLU is not differentiable, at least one point. Okay, so differentiable imply continuous. Fine. We can show it. How about Lipschitz continuity? And so that means differentiable is stronger than continuous. Lipschitz we know is also stronger than continuous. So how about between Lipschitz and differentiable, which one is stronger? Which one imply the others? So he said that differentiable imply Lipschitz. When the domain is compact, do we have any other objection or different idea? Hmm? Continuously differentiable. Okay, you can add more. But well, in general, what he says is that differentiable imply Lipschitz, right? Any of you think that Lipschitz imply differentiable? But in here in politics, here, how many parties that we have?
Two big parties, and the third one is mid-size, and there are many.
Oh, I see. So it's similar to the US. Actually, it's more than the US. You have to only have two. There's no mid-size. Yeah. I'm asking that it's not just an out question. I mean, it's not like I'm just automatically go to politics for anything, right? So typically, I have a question. I have like I have two type of answer in the class, and it just only remind me. Yeah, that's why we have only two party in politics, right? So that we can debate, right? And then we can vote for actually which one is wrong, which one is right. Anyway, it sounds like we have only one party here, not two party. Yes, actually, yes. Differentiability imply Lipschitz, but if you learn a little bit deep later, right? If you learn a little bit deep math later, especially measure theories, Lipschitz continuity in fact imply differentiable almost everywhere, right? If you actually ignore the set of measures zero, then differentiability and Lipschitz actually not different. Okay. Anyway, just a fun thing to chat with you. Okay, so if you if you assume that your function differentiable, right? Then the Lipschitz constant is actually less than or equal to the the maximum of the derivative, right? And of course, because you require stronger, you can. This is actually easy. I mean, show it homework for you. Show that the Lipschitz constant is less than this, right? If your function is differentiable. Okay. And of course, I do maximum here is on this maximum. If you do mathematics a little bit, this maximum it does not hold unless f prime is continuous. Okay. So if a continuous function, again, it's just math, just for fun here. A continuous function on compact sets achieves maximum minimum always. What is the theorem that says so? What I'm trying to say is that this, what I wrote here is actually meaningful. I don't use supremum, I use max. I don't use supremum because in this case, supremum and max are the same. Which one say again? Extreme theorem. Yeah, actually, when somebody say extreme, they actually didn't do really a good way of actually acknowledge people. Actually, there's a very famous person who actually established that theorem, and we have to remember his name. Weierstrass, that's correct. What Marco said is correct. Weierstrass theorem. Right? If a functions, continuous function on compact sets, right? Regardless, this is in general topology as well, right? Not only on Rn, right? Any topologies, a continuous function on a compact set always achieve minimum maximum, right? That's a well-known Weierstrass theorem. Just I think it's good to chit chat with you on a different perspective. Weierstrass. Okay, so this meaningful if the derivative here is continuous, right? If it's not continuous, then this is not meaningful because it's only meaningful for the continuous functions. Anyway, you can show that, and therefore the same thing, right? For differential functions, if you want epsilon error, then the number of neurons is 1 over epsilon. And this is actually, you see, that is also the kind of problem with neural network. And you're going to see later, we still have 3 more lectures, right? You're going to see this actually related to Monte Carlo method as well. And you're thinking about number of sample points, right? So the error is actually approximately you're going to see actually a little more than this, right? Monte Carlo is the square root of n. This is at least kind of, seem like a little bit better than Monte Carlo, right? But you cannot get better than this rate. You cannot get it better than this rate. So if you want, you see that the number of neurons can be increased very quickly, right? Because in order to get 1 digit accuracy, you need 10 times more neurons, right? Because this is 10 to the negative 1, this is going to be 10. 10 to the negative 4, this is going to be 10,000, right? So every digit accuracy that you require, you need to make your network 10 times wider. So it's not very actually impressive result. But that's not what we care about, right? We care about, if you give me enough, if you wouldn't have enough number of neurons, then we actually can approximate well. And that actually lead to the complaint about saying that every digit accuracy that you need your 10 times bigger, right? And in theory, right, if you want this is smaller, the number of neurons actually go to the infinity very fast. You see that? It grows so fast. And that's the main complaint about shallow network, because we have only 1 layer, right? 1 layer, 2 layer, or less than 2, or about 2 or 1 layer, it becomes shallow neural network. And this is the main reason for doing deep neural network. Deep neural network actually is actually more efficient because you don't need to grow that fast, right? But it's again, it's not It's not, it's just I give you a motivation to look into, right? And the reason why we need deep neural network, because shallow network is not efficient. This result also tell us, because every digit that you want to attain, you need 10 times wider network. So it's grow very fast. Okay, so I chat with Professor Chung Hao a little about why deep is actually better than shallow, right? But there are papers on that. I would love you to encourage you to look. But I just give you the motivation why this our result also tell that we should go to deeper, right? Deeper, you have more non-linearity, and the non-linearities actually can overcome the dimensionality. So this is actually another thing in mathematics that we do all the time that I want you to have as well. This is a quite generic principle in mathematics. If you have very non-linear problem, right? And we have very non-linear problem, then typically there's a way to do transformations. You can turn that nonlinear problem into less nonlinear or linear problem by simply increase the dimension, by doing change of variables, by increase dimensions. So basically you trade the complexity for high dimensionality. And that's a very, very actually quite universal principle in mathematics. So you lift the original problem in low dimension to high dimension. But the good thing that you achieve is that you remove or you make the nonlinearity less. Right? That's actually very popular, and actually there's also called lifting techniques, right? And if you look at some of you do convolutional neural network, you say upsampling and downsampling. Upsampling, why? Upsampling does because you lift into higher dimension, things become less nonlinear, and it's easier to learn. It's easier to work with higher dimension, but the trade-off is that you are in higher dimensions, right? So no free lunch. And in machine learning, there's a famous no free lunch theorem as well, right? There's no free lunch. And that's how typically we look at, right? If you have some problem difficult, we live into high dimension and we work there. And that's actually the kernel approach. What we actually don't cover in this class, in my standard machine learning class, I cover kernel learning, right? Kernel method is actually lifting in very high dimension. When you lift into high dimension, things become actually quite linear, actually linear. Then you can learn much more easier there. Okay, so that's the typical way that we do. But in this case, you can think the other way around. Why deep is actually better? It's actually the other way around, because this say that shallow is a very high dimension. You need a lot of neurons, right? So, but a deep, you don't need that much layer, because deep is very nonlinear, because you do composition of nonlinear, right? Nonlinear composition of nonlinear. So deep actually very nonlinear, and if you agree with me that nonlinearity is equivalent to high dimensionality, but linear and easy, right? Then you actually can also see why deep actually is better as well, intuitively. Everybody else see that? Okay, it just give you some motivation, some a little intuition why deep is better. But there's the paper on that. Just go Google and you see it. There's actually at least a couple of papers there. I can send them to you if you could not find it, right? Just send me email. Okay, so that result is very important, right? You see, that's very simple. We should do standard math, and when it tell this result tell us so much, right? These results tell us so much by limit ourselves into a symbol class of activation function, by symbol limit into a symbol class of function. This result tell us so much about neural network, right? And what we should do in practice. Okay. Not only it showed that neural network actually universal, right, or dense, but also tell us a lot about practical issue. Okay, so of course you're gonna ask me, okay, if you want to do a proof, for any activation function. How should I do it? Right? What we show here is just ReLU. If you want it, and if you Google, you're gonna be you're gonna find it's very difficult, right? Because each in the literature right now, each activation function people develop different proof, and some of them can be very technical. I think some of you sent me an email yesterday about the original paper by Sibenko. Right? Sibenko is considered to be the first who actually provide the proof for the universal of sigmoid function. And what he used is actually Horn-Barnard theorem, right? Some Stone Wear stress, actually Wear stress theorem to prove, and so on. So very, very deep functional analysis. What in these papers that I show is that I provide a seamless possible framework, unifying one single proof that work for all activation function, right? But it's not free. It's not for free lunch. It requires some knowledge. It requires some knowledge about symbol knowledge in functional analysis, symbol knowledge in numerical analysis, and some symbol knowledge in probability. Okay. But if you are interested in more, you can read it. But we have one single theorem that works for all, right, and valid for most of activation functions. And some activation function does not have universal, and if it could fall into our framework, it's automatically have the proof as well. The only two activation function that is not in the framework that I consider is the sine and cosine function. Sine cosine function is actually weird. We don't know. I don't know how to deal with that. Of course, we can discover new activation function as well, and non-asymptotic. You don't know. Professor Chung Hao may know better, right? So in statistics, we have two types: asymptotic and non-asymptotic. I will talk about a little bit about that when we talk about laws of large numbers, right? When we talk about probability. But yeah, if you are curious, you can Google around, or you can take a look at my papers. I also do a reasonable overview of the current state of the art of universal approximation theory. Okay, any questions before we move to the next thing? So that's it for the universal theorem. Yes. Oh, sure. Yeah, that's very good, right? That's a very good question. What I show you here is just one dimension, right? But if you want to do multi-dimension, just a tensor product, right? So by use tensor product, that's enough. Tensor product, you look at me very strange, right? So tensor product. One way to do is easy is the tensor product. If you know, right? If you know the result for one dimensions, right? Then by tensor product, automatically the result actually valid for multiple dimensions, right? By basically you stack the dimension by dimensions, right? So because think about this, the easy thing about this now, what I show you is 1D, right? How do you go from 1D to 2D? You just need to multiply the approximation in this direction and multiply by this direction together. That's called tensor product. Okay, so you do ReLU in the x direction, ReLU in y direction, and you can see that you multiply two, right? Then you can get it. But that's a little bit detailed. But the answer is yes. That's easy. It's straightforward to do multidimensional, especially on compact sets. Okay, yeah. Or you can do directly on multidimensional as well. But this result is not limited by everybody. One dimensional is not limited, because we can easily extend it into a multidimensional. Any other questions? That's actually a very good question. Okay, so we cover the universal approximation theorem for a neural network. Okay, so the next thing is we're gonna do today. Unless you have questions, I'm gonna go to the more writing today, okay? Okay. Okay, so we're gonna do a new, we're gonna start a new thing today. But so for the next 20 minutes or so, or 15 minutes or so, right? 15 minutes, we're gonna do a motivation on uh, why we need optimizations, right? We haven't talked about we talked about optimizations. We talked about neural network, and it sounds like it has nothing to do with each other yet, right? We spend some time. Actually, I should have done this first before I introduce the optimization to you, but it's okay. But it's okay. So thinking about, right? So the supervised learning, in the supervised learning, we're gonna talk about supervised learning today. And we actually even limited ourselves into a very special case, right? We limited ourselves f from x to r. So x can be anything, okay? So x can be anything, x to r, but we just look at the function in r. In fact, it doesn't need to be r either, right? Let me show from x to y. Maybe that may be even better. Is unknown functions. Is unknown functions, and I'm sorry, let me actually match the notation that we do from the lecture notes, right? So our F gonna be our neural network, right? Can be deep neural network. Remember, F is equal to what? F is equal to the R phi R phi, right? R phi combinations of the input X. That we call A1. So the first layer is A1X. And then we apply a sigmoid functions, right? And then we apply the A2 alpha activation, alpha transformation, and then we apply by another activation function. So if we want to avoid, right, to avoid on the parenthesis, let me do a composition so that you can see even clearer, right? So alpha transformation and then do compositions with the activation functions, and then another alpha activation function, second layers, and then activation function again, and then A3, right? And then so on, so on, and so on and so forth until AN, right? Until AN, AL minus one, AL minus one. Remember that we said we have L layers, and then we have sigma activation function, and then we have AL finally. So right now we just assume it's linear. It doesn't matter, right? We just say that the final layer is the activation function is simply identity. Doesn't matter. Doesn't matter at all. I mean, if you want, we can just do another sigmoid here. Doesn't matter. Okay, so this is our L layer neural network. L layer. Okay, so where AI X or AI, right? AI is the R phi transformation. Right. of the ith layer. Given as, it's given as. If you give it as an input, right, AI time any input, let's say y, right, it is equal to wi y plus bi. Okay, so this is a way matrix. Way matrix. This is the bias vectors. Bias vectors in general, right? Bias vectors, right? And both of these were, of course, automatically, right? We are in the I layer. This is the way matrix and the bias vector of the ith layers, of the ith layers, of the I layer, of the I layer, of the I layer. Okay, right? So we don't know. When we actually don't know, right? What we do is that we don't know. We, of course, do not know these weights and biases. Okay. So we're gonna define. We're gonna call H. I'm gonna call it H as a hypothesis space. Hypothesis space, which is nothing more than space on F. Space on F, right? F is deep L layer neural network. Define above. You think that's today? This room is a little bit hot today? Warm?
Yes.
It's warm, right? I think it's warm today. Unlike the other day, it's actually warm. Yeah. Okay, so that's a name that people use, right? Basically, this is F is a layer, right? Of course, you see, right? For each value of weight and biases, for each value of weight and biases, right? Then each of them define one function. So our function is parameterized, right? In other words, right? In other words, we just don't write explicitly, but in other words, we know, right? Know that clearly. The H is parameterized by parameterized by weights and biases of the neural network. Right. So actually, the neural networks. By the way, this is hypothesis space. Actually, the space is actually not correct, right? The hypothesis space is not a vector space. It is not a vector space. We're not a vector space. Why is that? It's not a vector space. It's not, by the way, it's not a standard vector space, right? Remember that's and it's not even closed. It's not actually closed, and it's not convex. So this space is actually a problematic space. So you see that if I vary W, right? If I vary W's, if I vary W's, if I vary W's, then I have different function, right? For different sets of W weight and biases, I can have different functions. And they don't actually form a vector space, okay? They don't form a vector space. That is important. That's something that we need to know very clearly. It's unlike traditional objects that we do. We work in a linear vector space. It is not. It's not. It's not a closed, even a closed set. So that's why doing learning in machine deep learning in particular is difficult because the space that we look at is not traditional easy space that we're looking at. Okay, so I would like you to think about it. Why that is not the standard linear space. Okay, okay. So and actually that paper talking about that, right? To understand what is the space that the neural network in general, how it look like. Very nonlinear, non-convex, and it's not a vector space in the standard sense. All right, so all right, so for the natural questions. Okay, and actually I'm gonna ask you a question now, right? So you see what we just wrote down here, the function g is fixed, but that we don't know, right? On the other hand, a deep neural network is parameterized by weight and biases, by weight and biases. So that means for each one set of weight and biases, then I have different neural network or different functions generated by neural network, right? So of course I have infinite number of them. Okay. So, but I need to find an approximation to G, right? So what is the natural to find the best candidate or the best neural network? What's the natural way to do so? What's the natural to formulate a problem to hopefully find the best possible neural network? What's the natural way? I mean, that's us the only way, right? We have many choice. If you if you go to an ice cream, you're gonna spend $3 a scoop. You're gonna we're looking for which flavor that I like best. You only do an optimization all the time, right? What's the best? Or if I have $10, I want to buy the most material that I can, right? So what is a natural? What is a natural way to do so? Hmm? Just trying that? What optimizations? If I want my, of course, I make the question very vague, right? I make the question very vague. But as our human, or as us as a scientist, right? We have a pools of options. We always find the one to fight for the best one, right? So what do we mean the best one here? And a natural way is to what? To find f such that the error between f and g is smallest. That's one of the obvious best. Because we want to approximate g. What's the best? F. The one is closer to g. One of the obvious way, right? So if we measure this in some norm, and let me say, right, I'll assume clearly, okay, the questions. I have a question here. The natural question for us, okay, what is or which network is the best? among all in H. Okay, so the answers, unanswered. So I assume that G is in L2, L2x, right? That is the integral of G dx over x squared is less than infinity. That's an L2 functions, right? A function whose kinetic energy v squared. Think about that v squared. The sum of the total kinetic energy is bounded. So L2, assume that L2, then a natural formulations is, we're going to find f. Of course, f is a function of on the way basis. We find f such that the difference between the difference between the L2 norm, right? The L2 norm error between F and G. And how do we define the L2 norm? This is right. Double semicolon and equal is mean by definition, right? The L2 norm is defined by the integral over x of G minus F minus G dx. And we want to find F in H such that this is minimum, the error is minimal. So very natural, natural formulations. Okay, and you see, right? You see immediately that'll lead to the, this is generic, but this on the other hand is equivalent to, saying that this is minimizations of on the WI. Remember that we have a lot of WI and BI, such that the error between F and G is smallest. I from 1 ... to L. Okay, so we actually have a optimization problem to deal with. Okay, everybody, I think I didn't pay attention to the time. I'm sorry, we a little bit over time.